Hello, everyone. Welcome back. We are finishing up Chapter 18 in Fundamentals of Inorganic Glasses. Last time we introduced some of the fundamentals of glass strength and toughness. Today, we're going to focus on different methods for improving the strength and the fracture toughness of glass. So I would like to start off today with just a little brief review of the last lecture. Remember last time we introduced the Orwan expression for the ideal strength of a brittle material. And what we saw from this expression is that in the absence of flaws, the theoretical strength of a silicate glass should be on the order of 35 gigapascals. However, this is much larger than the observed practical strength for any real glass product, and the reason for that is the presence of flaws either in or on the glass product. Inglis developed the initial criterion to account for the concentration of stresses that occurs at crack tips. Inglis considered an elliptically shaped flaw in the interior of the specimen and showed that the concentrated stresses at the crack tip could be given by 2 times the applied, in this case tensile stress, times a geometric factor that depends on the length of the crack as well as the radius of curvature, where longer cracks and sharper cracks both act to increase the concentration of stresses at the tips. And basically what this leads us to understand is that the distribution of strengths that are observed in glasses goes back to the distribution of flaw sizes. Griffith had some more of the pioneering work in this area. Griffith considered that most of the flaws are not in the interior of a specimen, but on the surface due to handling and due to damage that different products can receive just within their everyday use. And that this damage can lead to a distribution of flaw sizes. Some of them are short cracks, some of them are longer cracks. And the key is that the strength of a glass product is governed not by the average crack size, but by whichever crack is the most severe, whichever is the longest, sharpest crack that leads to the greatest enhancement of tensile stresses at that crack tip. This is the weakest link theory. So that what this is saying is that the strength of a glass product is limited by whatever the worst flaw is. We also introduced the concept of a stress intensity factor. The stress intensity factor is given by K, and that is equal to the applied stress times this factor, which is the square root of the pi times the length of a crack C. And then the critical stress intensity factor is K with a subscript C, and this is where fracture occurs for a given length of the crack. So this would be the stress at failure times the square root of pi times C. The units of the stress intensity factor are megapascals times the square root of meters. And the critical stress intensity factor for mode 1 failure, this opening mode of failure, is defined as the fracture toughness of the material. That is denoted as K1C. K because it is a stress intensity factor, C because it is the critical stress intensity factor, and the Roman numeral 1 here is because this is defined in mode 1 failure. And the typical fracture toughness for a silicate glass is on the order of 0.7 megapascals times the square root of meters. Now, putting all of this together, what this means is that if our goal is to improve the strength or toughness of a glass, we have different ways that we can go about doing this. One is to reduce the severity of the flaws, thereby reducing the stress intensity factor K1. Another way would be to apply a coating to the glass to reduce the risk of surface damage. That would reduce the crack length C. Another way would be to increase the fracture toughness K1C by introducing mechanisms of crack pinning, deflection, or crack tip shielding. And another way would be to introduce a compressive stress in the surface of the glass This would increase the applied stress sigma sub A required to reach the failure level of sigma sub F. So all of these are valid options for improving the mechanical performance of the glass, and these options lead to different strengthening or toughening methods that I'm going to cover in this table shown on the current slide. One of the commonly used processes for strengthening glass is thermal tempering. This involves taking a sheet of glass and applying a particular thermal history such that there is a thermal history mismatch between the interior of the glass and the surface of the glass, and that creates a compressive stress layer in the surface of the glass. Advantages are that this is a relatively fast method, and it results in relatively thick compressive layers, so it provides a pretty good enhancement in the practical strength of the glass. Disadvantages are that it is difficult to accomplish this for thin glass or for any type of kind of non-plate geometry. It also requires a glass composition that has a high enough thermal expansion coefficient to be able to get the mismatch in thermal strain. Another method is chemical strengthening. This is an ion exchange method. This works well for thin glass. And it works well for glasses that have relatively low thermal expansion coefficients, provided that there's enough alkali in the glass to do ion exchange. Disadvantages are that it is slow and that the compressive stress layer is relatively thin compared to that which is obtained from thermal tempering. Acid etching is a way to reduce the severity of flaws. This can give high strengths that are possible immediately after acid etching because the flaw sizes have been reduced. However, additional surface protection would be required in order to maintain that advantage upon future handling. Likewise, with fire polishing, this is a fast way to basically apply a heat, apply like a torch to the glass surface to reduce the severity of flaws by inducing viscous flow that shortens or blunts the flaws. No washing is required as in acid etching. However, this is a difficult method for thin glass, and likewise, additional surface protection would be required in order to maintain that advantage in mechanical performance going forward. Lamination is another strategy. There's different ways to do lamination that we're going to cover. This offers good reliability and safety, but there is a cost associated with that and a weight associated with having multiple layers and the laminated piece. Ceramming is another option. So take your glass and turn it into a glass ceramic by having controlled nucleation and growth of a crystalline microstructure. This is a really effective way to increase the fracture toughness of your glass by turning it into a glass ceramic. Disadvantages are the cost associated with the heat treatment that is required, and there is a potential loss of transparency of the crystals become of the same order, length scale as the wavelength of visible light. And another process is applying coatings. These can either be hard coatings or soft coatings, so ceramic or polymer coatings. The advantage is that they protect the surface from the introduction of damage. Disadvantages are that it requires an additional process step to do that, and the application of the coating changes the surface properties of the glass. So let us start off with tempered glass. With tempered glass, what happens is that we heat up the sheet of glass and then cool it down rapidly. And the outer parts of the glass go into, they pass through the glass transition before the interior of the glass, and therefore they have cooled into a solid-like state first, while the interior of the sheet of glass is still in the molten state. And so the interior wants to contract more upon cooling through its slower path, and that pulls the outer part of the glass into compression. And that compression is balanced by a tensile stress in the interior of the glass. So if we plot the stress profile here as a function of going through the thickness of the glass sheet, what we see is that there is a compressive layer at either of the outer surfaces where there's a maximum incompressive stress at both of the surfaces here on the top and the bottom. As we go into the interior of the glass, that compressive stress decays, um, following a parabolic type profile. It passes through this zero crossing point of stress, and then it enters into a tensile regime in the interior of the glass. And with this stress profile, if you integrate the compressive stress at both surfaces, so integrate these kind of approximately triangular regions here at the upper surface and at the lower surface, that integrated compressive stress must be balanced by the integrated tensile stress in the interior of the glass. And so this part here in the interior, this kind of semicircular shape here in the interior, that stress exactly balances out the integrated stress of the compressive regions. What we see with thermal tempering is that you've got a relatively deep penetration of the compressive stress. It goes about 20% of the way in from either side. And so that is providing pretty good protection against both the introduction of new flaws and the propagation of existing flaws. So basically, if you have any crack, any surface flaw that stays within this compressive region, then you are relatively safe against failure of the glass. However, if that flaw becomes long enough that it penetrates through this zero crossing point of stress and then into the tensile region, that's where the glass will fail. And so you can think about this compressive stress region as being like an armor that is on the glass, where if you want to introduce a flaw or propagate a crack, you have to overcome not only the intrinsic strength of the glass itself, but also have enough stress to overcome that additional compressive stress that is at the surface. And so the magnitude of the compressive stress at the surface is kind of like the strength of the armor, and this location of the zero crossing point of stress, this depth of layer of the stress, that is like the thickness of the armor. And so the greater the magnitude of the compressive stress and the deeper this depth of layer, that corresponds to the crossover between compression and tension, that provides better mechanical performance. Now, with thermal tempering, this follows a parabolic stress profile. With chemical tempering, and I'll get into more details about this later in the lecture, with chemical tempering, the stress profile follows a complementary error function shape, and this leads to a higher compressive stress at the surface, but a shallower depth of layer. So when comparing chemical tempering to thermal tempering, chemical tempering gives you a greater magnitude of compressive stress at the surface, but the compressive stress layer is not as deep as thermal tempering. And so there's some trade-offs there in deciding whether to use chemical tempering or thermal tempering. Now, with thermal tempering, the amount of stress that you get depends on the thermal expansion coefficient of the glass, because this is based on a differential cooling between the interior of the glass and the surfaces of the glass, where that differential cooling translates into a differential strain between the interior and the exterior. And the magnitude of that strain is governed by the thermal expansion coefficient. So thermal tempering is especially useful for glasses that have high thermal expansion coefficients, such as soda-lime silicate glass, and it is especially useful for relatively thick pieces of glass, because with thick pieces of glass, you're able to set up a larger differential cooling between the interior and the exterior. As you go to thinner pieces of glass, that difference becomes less, and the amount of compressive stress that you can get from thermal tempering is compromised. Now, when we consider when glass actually breaks, we can see different types of fracture patterns in that broken glass. For example, if you have an annealed glass window and somebody throws a rock or a baseball through the window, you might get a fracture pattern as shown on the left. And this is kind of a starburst fracture pattern here. And the reason for the starburst fracture pattern is that there's a lot of energy that is being imparted into the glass from the rock or from the baseball that is actually more energy than is required to introduce just a single crack or just two cracks. And as a result, the glass needs to release this energy in some other way. And the way that it does that is rather than just having a single crack that goes through this, there are multiple cracks that form all at that same origin of impact from the rock or from the baseball. And as a result, all that excess energy from the rock gets converted into surface energy by forming a large number of cracks that propagate out radially from the origin. Um, and therefore, this starburst pattern here is a direct result of having excess energy coming from an external source, from this rock or from this baseball, that is then transferred to the glass itself. So a lot of cracks are formed at that point of impact, and then they all propagate out radially. Now, if you have a laminated glass, in this case, what is being implied is that there is some polymer interlayer that is kind of holding the two panes of glass together. And instead of the pieces being broken and coming down to the bottom, they're being held together by that polymer layer. So you can see this kind of webbed pattern here. And the other thing to note is that you have both a starburst pattern here from all that excess energy, but there's also some crack branching that is due to compressive stresses. And that really gets magnified when you go to thermally tempered glass, where there is a significant amount of tensile stress in the glass itself. And when a thermally tempered glass breaks, you get very small fragments. You get this kind of dicing behavior where the glass is not breaking into large shards, but it is dicing into these very small pieces. And the reason for that, it goes back to the stress profiles. So if you break a thermally tempered glass, what that means is that the crack has become so long that it penetrates through the compressive stress region and gets into this tensile region. So the crack is long enough to go through the depth of layer, and the crack tip is in the region of tensile stress. Now, the difference between compressive stress and tensile stress is that compressive stress wants to close the crack. It wants to pull the glass together and close the crack. So if the crack stays in the compressive region, you're safe. But if the crack penetrates through the compressive region and into the tensile region, tensile forces want to pull the material apart. Tensile forces want to break the glass. And if the crack goes into that tensile region, it's just enabled all those tensile stresses to be released. And those tensile stresses are going to accelerate the crack tip. They're going to make the crack propagate faster. And the crack velocity is going to increase until it reaches the terminal crack velocity for that material. And the terminal crack velocity, meaning the fastest that a given crack can propagate, is governed by the speed of sound in that material. And for a typical silicate glass, that terminal crack velocity is on the order of 2,000 meters per second. When that happens, there's still a lot of tensile energy that needs to be released from this tensile layer. So there's a lot of tensile energy that needs to be released, and it needs to be released faster. But the crack can't propagate any faster because it's already achieved its terminal velocity governed by the speed of sound. So what is the way for the crack to release energy even faster? The way to do that is for the crack to branch. And so when the crack hits that terminal velocity, the only way for it to release energy faster is for that single crack to bifurcate into two new cracks. Those two new cracks can then release energy at twice the rate until they hit their terminal velocities, and then they will bifurcate again and form four cracks, and then eight, and then 16, and so on. And therefore, this fracture occurs in a kind of fractal type of pattern, and that leads to a fragmentation of the glass into very small pieces. This is what's called frangibility. Frangibility occurs when a glass breaks into very small pieces as a result of branching of the cracks due to the release of tensile energy from the interior of the glass. Now, the next question becomes what governs the size of these pieces? Um, Basically, that is governed by the magnitude of tensile energy that is in the interior of the glass. If you've got a greater amount of tensile energy, that's going to accelerate the cracks faster. They're going to reach their terminal velocity sooner, and then they're going to branch sooner. They're going to branch at a smaller length scale. So the greater the amount of tensile energy in the glass, the smaller the pieces that you will ultimately get when it fractures. This is a feature not only of thermally tempered glass, but also chemically tempered glass and laminated glass. So any time when there is stored tensile energy, that balances the compressive stress energy that is put into the material. Now, what is the practical benefit of going to a thermally tempered glass? We have an improvement in the retained strength of that glass. The graph here on the right shows the modulus of rupture here. So this is the stress at failure for annealed glasses here. And this is as a function of the logarithm of kinetic energy of impact from silicon carbide particles. Basically, they took a sheet of annealed sodium silicate glass, blasted it with silicon carbide particles for different sizes and with different energies. And the greater the amount of damage that is done to the annealed glass, then the less stress that it can take before failing. And so that's why you'll see this decrease in the practical strength of the glass with that greater amount of damage. Now, if you do the same experiment, but instead of an annealed glass, there's a thermally tempered glass that has a compressive stress layer, you'll note that all of the strengths are shifted up because of that compressive stress layer. And also, it is able to withstand a greater amount of damage after being impacted by those silicon carbide particles. So not only is the base strength higher, but there is a less loss of strength after being impacted by silicon carbide. So thermal tempering is providing kind of a double advantage there, the additional compressive stress that helps prevent the propagation of damage, but it's also helping to prevent the introduction of damage in the first place. So there's some very practical benefits for introducing a compressive stress profile, such as through thermal tempering. Now, another way to help retain the strength of glass is to apply a coating. A coating will protect whatever the condition of the original surface is upon application of that coating. So any flaws that are there, any moisture, any roughness, that gets retained. It just gets hidden underneath the coating. If there had been some fire polishing or acid etching done first, then you'd start off with a better quality surface, and that better quality surface can then be protected through a coating. There are broadly two different types of coatings that are used for glass products: hard coatings, which are ceramics, or soft coatings, which are polymers. And hard coatings and soft coatings are often applied at different points in glass production processes. These are the so-called hot end coatings and cold end coatings. Hot end coatings are done, say, during a bottle manufacturing process or a sheet glass manufacturing process where the glass is still hot. A typical hot end coating would be tin oxide, which provides a hard surface to help prevent the introduction of damage into the glass. And after the glass is cooled down, there can also be cold end coatings, such as lubricious silicone or polyethylene. These are meant to help reduce frictive damage that can occur. For example, if the bottles are rattling against each other, or if it is, say, pharmaceutical vials that kind of get pushed together in the glass manufacturing process, having a polymer coating to reduce the coefficient of friction can help prevent the introduction of frictive damage. So both of these are helpful means of reducing the damage that gets introduced and therefore increasing the retained strength of the material. An example of this, it shows the strength of coated glass containers after abrasion. This is showing the relative bursting pressure of a glass bottle, where the uncoated glass is normalized with a relative bursting pressure of 1. If there is a pretty thick hot end coating only, that burst pressure increases by a factor of 2.44. If there's a cold end coating only, it increases by a factor of 2.88. In this case, the combination of doing hot and cold end coatings really didn't provide any overall advantage. But if the thickness of the coatings is optimized, it can lead to a net advantage by combining both hot end and cold end coatings, where in this last row of the table, there's actually a threefold increase in the amount of bursting pressure that the bottle can take, having both the hot end and cold end coatings compared to the uncoated case. Now, another method for improving the practical strength of glass products is through lamination. There's different ways to do lamination. One of the common ways for safety glass and for automotive windshields is using lamination with a polymer coating between two sheets of glass, as shown in the upper left. This is a traditional 3-layer polymer glass laminate, where the typical polymer that is used as the interlayer is PVB, polyvinyl butyrol. And the advantage of this is that if the glass breaks, it is still adhered to the polymer layer, so the shards are not flying in people's faces. And it combines some of the beneficial properties of both the glass with its high hardness and high strength, and the polymer with its adhesive properties and higher toughness. So this is very good for safety applications. And another nice thing is that you can just take as made sheets of soda lime glass and then go through a post-processing step to create the laminate with the PVB interlayer. Another type of laminated glass would be where all 3 layers are glass. So instead of having a polymer layer, you have a glass laminate. An example of that in an everyday glass product is this laminated glass tableware. This is Vitrel laminated glass, and this is sold as Corel tableware products. Even though these might look like ceramics, these are actually laminated glass tableware where there is a phase-separated opal glass in the middle. It has a spinotally decomposed glass in the interior, and that's what gives it the white color. It's because of the microstructure that results from spinotal decomposition. And then there is a thin, clear glass that is applied as the cladding all around the plates, and that is pulled into compression, so it has a very high strength. It also has a high chemical corrosion resistance, which means that these laminated glasses will last a very long time, going through many dishwashing cycles in a dishwasher. You can also drop them and bang them, and they're actually very strong. And so that's why these laminated glass dishes have been so popular, so that they have much higher strengths compared to traditional tableware. And also because of their design, you can have all types of different designs that can be introduced as well. So they're aesthetically pleasing, mechanically strong, and relatively inexpensive to produce. They've got a lot of great properties going for them. Another way to make glass laminates is through this modified sheet draw configuration. This is a double fusion draw process. If you remember in our discussion of chapter 22 on the manufacture of glass sheets, one of the methods invented by Corning was the fusion draw method, where there's a molten glass that overflows both sides of a ceramic isopipe. The glass flows down on either side, fuses at the bottom, and then is drawn into a sheet. And an advantage of this process is that the outer parts of the sheet don't touch anything other than air, so you get really good pristine surface qualities. Well, one of the advances that Corning has made is the double fusion draw process, where there is a second cladding glass, where there's an isopipe placed on top of the core isopipe. There's a second glass composition that overflows that, and then that cladding glass overflows the core glass, which overflows this inner isopipe. So there are two ceramic isopipes with two different glass compositions, two different melters delivering a clad glass composition on top, a core glass composition on the bottom. The cladding glass overflows both sides of the core, and then it's pulled down into a three-layer sheet. So there's a cladding, core, and then a cladding. And the advantage of this process is that if you design the two glasses to flow in a similar way, so they have similar viscosity curves, but a mismatch in the thermal expansion coefficient, where the core glass has a higher thermal expansion coefficient compared to the clad glass, then a thick compressive stress layer can be generated right off the draw without any post-processing steps. So without any thermal tempering necessary, without any ion exchange necessary, just because of the differential strains resulting from the two different CTEs upon cooling, the cladding layer will get pulled into compression, and the thickness of that compressive stress layer is exactly equal to the thickness of the clad glass layer. And this is because as the laminate cools together, the core glass with the higher CTE wants to shrink more compared to the cladding glass. But once the clad glass passes below its strain point, it is frozen into the glassy state, and it is not allowed to shrink anymore. So as a result, the core glass wants to shrink more, but the clad glass doesn't allow it to. And so the core glass is pulling the clad glass into compression, and then the clad glass kind of stretches the core glass out into tension. So all of the clad glass is under compression. That provides is a constant level of compressive stress through the clad, where the thickness of that compressive stress layer is equal to the thickness of the clad glass. And so this gives you really good strengthening right off the draw without any post-processing steps. The only downside is that when this is cut, there is tensile stress that is exposed around the perimeter of the laminated glass sheet because of the exposed core layer. The core is under tension, and if this is cut, then that core is exposed, and that exposed tensile stress can be dangerous and compromise the strength of the laminated glass product. So there needs to be some sort of protection there by either applying a coating around the perimeter or having the laminated glass sheet affixed in such a way that the perimeter is not exposed. Now, another way to improve the mechanical performance of a glass product is by increasing the fracture toughness. And as I mentioned before, there's not much that you can do to improve the fracture toughness of the glass on its own because of its lack of a microstructure. So the best way to improve the fracture toughness is to introduce a microstructure. And the best way to do that is through ceramming. In other words, by having controlled nucleation and crystal growth to turn the glass into a glass ceramic. A couple of examples of that are shown here: a floor mica glass ceramic on the left, a mica glass ceramic on the right. And if a crack tries to propagate through any of these microstructures, every time it encounters an interface between a crystal and a glassy matrix, three possible things can happen. There can either be crack pinning there, or the crack is unable to go any further until the propagation direction changes somehow, or it needs to be deflected by the crack and increasing the amount of fracture area that needs to be created. So that increases the amount of fracture energy that's required to break it, or new cracks would have to be initiated at those interfaces. Any of these possibilities mean that more energy is required for the crack to propagate, and the greater energy that is required for failure to occur means that the fracture toughness of the glass ceramic is better than the fracture toughness of the parent glass. The downside to this is that there is a trade-off between fracture toughness and optical transparency, where you can get a greater enhancement of the fracture toughness with larger sized crystals. The larger sized crystals mean that optical transparency is lost because these interfaces are not only improving the fracture toughness, they're also acting as interfaces for light to be scattered. And if the size of the crystals becomes of the same order as the wavelength of visible light, then the glass ceramic will no longer be transparent, but it will be white in color. Now, another really popular way to improve the mechanical performance of glass is by chemical strengthening. This happens through an ion exchange process. And the way it works is that the as-formed piece of glass has some concentration of smaller alkali ions in it, such as sodium, could also be lithium. And then that as made glass is immersed in a molten salt bath, where that molten salt bath has a larger alkali ion in it, such as potassium. Usually the salt would be a potassium nitrate salt, and usually the salt bath treatment is done at a temperature of around 400 degrees Celsius. The temperature needs to be high enough that the salt is in a molten state and high enough such that the kinetics of the ion exchange process are fast, but the temperature has to be low enough so that it's below the strain point of the glass to make sure that the stresses that are generated during ion exchange are not also relaxed. So we have to keep the temperature low enough to suppress that stress relaxation process. Now, ion exchange is an entropy-driven process. When the glass is submerged in the molten salt bath, the smaller ions will hop out of the glass into the bath, and from an entropy point of view, they're much more likely to be replaced by the larger alkali ions from the salt bath. So in this case, sodium and potassium both have the same charge, so a charge balance is achieved, but the potassium ion is larger than the sodium ion. So even though there's charge balance, the local structure here in the glass was cooled in such a way that it accommodated the size of a sodium ion. The potassium ion is larger than the sodium ion, and so it wants to strain the glass network to pull it apart to allow more room for this larger ion. But the exterior surface of the glass where this ion exchange is happening is bonded to the interior of the glass, and that is not allowing for that expansion. And so as a result, the surface wants to expand, but it's not allowed to because the interior of the glass is pushing it into compression. So that's how this compressive stress develops through ion exchange, is that the concentration profile from the ion exchange process converts into a strain profile because the potassium wants to expand, but it's not allowed to expand, and therefore that strain profile gets converted into a stress profile. So the kind of sequence of events are concentration profile leading to a strain profile, which gets converted into a stress profile, and that creates a compressive stress layer, which provides a barrier to fracture. Now, the simplest physical model for the ion exchange process considers the salt bath to be a semi-infinite source with a constant surface concentration of the potassium ions given by C surf. If there is any initial concentration of potassium in the glass, there's also the C base, which is the concentration in the as-formed glass. This often is zero, but it could be non-zero. But in either case, the concentration profile between the surface concentration and this base profile, whether it's zero or non-zero, that functional form is a complementary error function, which has the shape shown here. So the concentration profile follows a complementary error function shape, where this D here, the diffusion coefficient in Fick's second law, is the interdiffusion coefficient for the exchange of the two alkalis. So in this case, the interdiffusion coefficient for the exchange of potassium for sodium. And solving The diffusion equation, Fick's second law, under these conditions gives you the solution of a complementary error function. Now, that concentration profile, which follows a complementary error function, gets converted to a strain profile, and the constant of proportionality between them is B, this coefficient B, which is called the network dilation coefficient, also known as the linear network dilation coefficient or the Cooper coefficient, in honor of the late Professor L. Cooper, who was a pioneer in understanding the basics of ion exchange physics. Now, this network dilation coefficient B tells us how much strain that we get per unit of ions exchanged. You can think about this as being analogous to a thermal expansion coefficient. A thermal expansion coefficient tells you how much linear strain that a material undergoes per degree change in temperature. The network dilation coefficient B tells you what is the linear strain per unit of ions exchanged. So for every mole percent of ions exchanged, how much strain do we get? And that is the coefficient B, and that gives us a strain profile, epsilon of Z, going through the thickness of the glass. Now, this strain profile gets converted to a stress profile, and if it is a planar geometry here, the strain profile gets converted into a stress profile by multiplying by the Young's modulus over 1 minus the Poisson's ratio. And all of this needs to be normalized such that the integral of the stress across the entire thickness ends up being 0. This means that all of the compressive stress is balanced by all of the tensile stress. So this entire integral here must go to 0. This is the so-called force balance condition. So all of the forces acting in the compressive manner are balanced by the forces acting in the tensile manner. And so integrating the stress profile across the full thickness gives 0. And the equation then that this gives is that there's a difference between the average concentration and the local concentration of stresses, such that if the concentration is higher than the average, this gives a negative number, which is a compressive stress. If the concentration is lower than the average concentration from that profile, then it's a positive number, and this indicates tensile stresses. And because of the subtraction here, this is what causes the integral to go to 0. And you can see the various parts of this equation are the concentration profile relative to the average. That gets multiplied by the network dilation coefficient to convert to a strain, and that gets multiplied by E over 1 minus the Poisson's ratio to convert the strain to a stress. So some things to note are that this obeys the force balance condition. This also means that the stress depends on the thickness of the glass L, and basically that the stress is proportional to the concentration profile, but with some additional shift in order to obey this force balance condition. And the stress profile would look something like this, shown on the lower left, where one end of the glass is here, one surface, the other surface is on the other side. The thickness of the glass goes across widthwise. There is compressive stress at both surfaces, both the left surface and the right surface. That compressive stress decays following a complementary error function shape. And all of the integrated compressive stress at both surfaces in these triangular regions on the left and right, that area is balanced by the area of the integrated tensile stress shown in the yellow shaded region. That means that there is a 0 crossing point of stress on both sides, where we transition from a compressive stress regime into a tensile stress regime. That is called the depth of compression or the depth of layer, DOL. And so, as I mentioned earlier, this can be thought of as enveloping the glass with some compressive stress armor, where the key parameters are the magnitude of the compressive stress at the surface of the glass, the CS, compressive stress. This is like the strength of the armor. The depth of the compressive layer, the DOL, which is like the thickness of the armor. And since all of this integrated compressive stress needs to be balanced by integrated tensile stress, the other relevant parameter is the magnitude of the tensile stress in the middle of the glass. This is the so-called central tension, or CT. So all of these compressive stresses, CS at the surface, get balanced by the tensile stresses. And this applied, so if we apply a tensile stress now to the ion exchange glass, the applied tensile stress needs to overcome the compressive stress before the cracks can initiate and propagate. Now, if we have a concentration profile through the ion exchange process shown here, this is measured with EPMA microprobe, where we've got the surface concentration of the potassium here. And then for longer ion exchange times, these are the ion exchange times in hours, you can see that we get deeper and deeper penetration of the potassium ions into the glass. And typical ion exchange times would be on the order of, say, 8 hours or 12 hours. Now, some interesting physics, it relates to the composition dependence of ion exchange. On the left, I have 3 different glass compositions that were subjected to ion exchange at 3 different temperatures, 370, 410, and 450 degrees C. This is plotted on 1 over absolute temperature axis. And on the y-axis is the log of the interdiffusion coefficient between the potassium to sodium ion exchange. And the interesting thing here is that you'll see that the slopes are the same for all of these compositions, indicating that the activation barrier for the ion exchange process is the same for each of these glass compositions. And all that is changing is that these diffusivity curves get shifted up and down. What this means is that the activation barrier is not really what's changing from composition to composition, but rather the prefactor of the Arrhenius curve, which is governed by entropy rather than activation barrier. That's the key part that changes with composition. And in fact, if we plot the from the slope here, that gets us the activation barrier for the ion exchange process. Each one of these points here is a different glass composition. And what you'll see is that the activation barrier for the ion exchange process is not changing outside of error bars for any of these glass compositions. And in fact, it's on the order of 1.1 electron volts. And on the x-axis, what we have is the activation barrier for viscous flow. And this is showing that we can change the activation barrier for viscous flow, changing the viscosity without affecting the activation barrier for the diffusion process. And what this is indicating is that some of the key physics here governing the ion exchange process is the breakdown of the Stokes-Einstein relation. The Stokes-Einstein relation would relate the diffusion process to viscous flow by assuming the same underlying physics govern both process. If the Stokes-Einstein relation were true, then the activation barrier for diffusivity and viscous flow would be the same. But what we've shown here is that they are varying completely independently of each other. And so when designing an ion exchange glass, it's important to note that there is this complete breakdown of the Stokes-Einstein relation. Some other interesting physics here are that if you consider the compressive stress versus glass transition temperature for a bunch of these different glass compositions, you could see in the left-hand plot that there may be some relationship between the two. It looks like a fairly noisy relationship between compressive stress and glass transition temperature. This is if you plot the y-axis in terms of stress, but if you use the measured Poisson's ratio and Young's modulus to convert the stress description into a strain description, and then plot the linear network dilation coefficient, or Cooper coefficient, on the y-axis instead of the stress. So instead of a stress description, we now have a strain description in terms of the Cooper coefficient on the y-axis. All of these points collapse onto a single master curve with respect to the glass transition. And what this is indicating is that the same physics that governs the glass transition temperature, which is the underlying topology of the glass network, that topology of the glass network is also governing the Cooper coefficient and governing the strain response with respect to ion exchange. So if you're interested in learning more about that, you can read more at this paper that is referenced at the bottom, Accelerating the Design of Functional Glasses Through Modeling. Either way, the net result is a dramatic improvement of the strength. This shows actually a chemically strengthened soda-lime glass versus a chemically strengthened Gorilla Glass. Soda-lime can be ion exchange, but it's not particularly good for ion exchange because it is not designed to be good for ion exchange. Gorilla Glass is an aluminosilicate glass. With an aluminosilicate glass, there is a strong glass network, but at the same time, the sodium ions are not forming non-bridging oxygens. Instead, the sodium ions are providing charge compensation for the alumina units. And this means that they're not tightly bonded to the glass network, which means that the alkali ions are highly mobile, at the same time as providing a strong glass network. And as a result, Gorilla Glass is much more effective at ion exchange compared to soda lime, so that the overall strength is significantly higher. And you notice that the line here is steeper. That indicates a higher Weibull modulus, so a much lower scatter and strength, which is another major advantage of Gorilla Glass. Now, in some of the newer Gorilla Glasses, starting with Gorilla Glass 3, another feature that had been introduced to help improve the mechanical performance is intrinsic damage resistance, which was trademarked as native damage resistance. And this is actually including boron in a threefold coordination state in the glass. As you know from Chapter 5, boron can exist in either trigonal configuration, B3, or tetrahedral configuration, B4. If it is included in the glass in trigonal configuration, that creates a more open structure without getting in the way of ion exchange and also allowing for the ability of the glass to compress. And so with these glasses that have native damage resistance, there's an additional benefit beyond just the compressive stress that there is another mode for the glass to absorb energy beyond just creating cracks. The left-hand side shows glass under either Vickers indenter on the top or a scratching across the surface with a Vickers indenter. And you can see that cracks develop as a way to release energy. With native damage resistance, there is actually a plastic deformation mode that gets introduced into the glass where it's able to compress permanently by densifying around the threefold coordinated boron and having dynamic conversion of the boron from threefold to fourfold coordination. This dramatically improves the scratch resistance and the damage resistance of glass products. And so these newer Gorilla glasses that have this feature have multiple advantages. There's not only the compressive stress advantage of ion exchange, there's also this native damage resistance. And all of this means a significantly higher resistance to the introduction of damage and the propagation of damage. All right, that is a summary of strengthening and toughening mechanisms. Next time, we are going to consider thermal properties of glass, specifically the heat capacity and thermal conductivity of glass. All right, if you've got questions, let me know, and I'll see you next time. Thanks, everyone.